好，非常感谢大家在非常短的这个10天左右的会议通知的情况下出门到场。这个会议呢是我们田老师亲自要求我们大家进行举办的。然后我们首先邀请田老师给我们致辞。
There's a few people who may not speak Chinese in the audience. So anyway, welcome to Beijing International Center for Mathematical Research. And so this center was established in 2005. Now it's this year actually we will celebrate the 20th anniversary. And this center has the wonderful purpose of this center is to have a platform for academic exchanges. So I guess today's event is a very important event for the center, and also it's as you will see it's well received. So anyway, so it's we are welcome Deng Yu. I'm very happy and Deng Yu accepted our invitation to give this series of lectures here. So this is not this whole workshop is dedicated, or this whole week is dedicated for this recent work of Deng Yu and also his collaborator, I guess Marshall and other person. And at least 2 of these authors are here this week to give many lectures, and also some other people in related fields will give some lectures. So hopefully, I guess for many Chinese or many people in the audience, they probably come because this is well circulated in the China media. Chinese media, and they did very important work. I guess that's not strong enough words for his work, and hopefully this whole week will provide a platform for Deng Yu and his collaborators to present their proof and their works, and also hopefully we actually also arrange some people to take notes, and we want to, since this is extremely important work, certainly our students or our faculty or colleagues were happy to see and to see how this is proved, and to learn maybe some techniques or for their work. And also for our students, I think this is an opportunity to see anything is possible, just try harder and work harder and having a good goal and a high goal and keep working, and you will succeed eventually, and at least you have a chance to succeed eventually. So anyway, so also maybe in last so today is a very nice day, and Beijing is now turning to its spring comes. So I guess many of you came from other places, and I hope while you enjoy Deng Yu and his collaborators' talks, and also enjoy the beautiful campus of Peking University. And so anyway, and also if you want to learn something more about our center, and I guess some of my colleagues here, and they will give you more information
Okay, so is it everything good? The sound, the voice is good? Okay, thanks for the kind introduction. So I'm very happy to be here to present our recent work. This is collaborative work with Zahar Hani and with Ma Xiao, both from University of Michigan. And basically, in this recent work, we have been able to derive the Boltzmann equation, the Hart-Sphere-Boltzmann equation, for arbitrary long time from the Hart-Sphere system. And as a consequence, we have also been able to derive the corresponding, kinetic limits again from the Hart-Sphere system. Okay, so the plan of this week. So we have 5 2-hour lectures, and today I'll be talking of today, and on Tuesday and Wednesday my collaborator Martial will talk. Will give 2 lectures, and then I'll finish off on Thursday and Friday. Okay. So maybe we can start. So let me first by introducing what is the so-called Hilbert-6 problem as mentioned in our second paper. We start with the So this is so-called Hilbert-6 problem. If you look at Hilbert's original paper in 1900, you'll see that when describing this problem, he had a kind of very broad and huge title, which is called the mathematical treatment of axiom of physics. And with that title, if you think of it, if you interpret that title, then it essentially could have included all of modern mathematical physics. And of course, at the time of 1900, when Hilbert, talked about this, he had, the development of the modern mathematical physics was still pretty limited. And with the 20th century, nowadays the whole mathematical physics had developed kind of far beyond what Hilbert could have imagined at that time. So because of this, it's obviously not possible to solve that statement of Hilbert-6 problem at the full experimentation of mathematical physics. And of course, this is not what we're going to do in these lectures. However, in the original paper of Hilbert, he actually proposed 2 specific problems that actually were related to the time, to the experimentation problem that he was interested at that time, which was the full rigorous justification of the kinetic theory as developed by Boltzmann, earlier by Maxwell in the 1870s. So this justification. So actually, Hilbert mentions 2 particular problems in his paper. One was the justification of the foundational probability, and second was this one. But both are related to this development of kinetic theory and statistical physics. So actually, what Hilbert specifically called in his paper is that the passage from the atomistic view to the motion of continuum via Boltzmann's theory. And this is the main topic I'm going to present. We are going to present in this week. Okay. So basically, starting from the time of 1860s to 70s, and with Hilbert's advertisement in the 1900s, and with the full development in the 20th century, nowadays people have a kind of a basic canonical understanding of this process. How do we go from atomistic view to the motion continuum? And by the motion continuum, we usually understand it as the motion of a fluid, the fluid equation, like Euler and the Navier-Stokes equations. Okay, so we have this big picture. Okay. Actually, let me write it. Let me write it here. Okay, so there are 3 levels. So the whole picture is kind of a 2-step process. We'll have 3 levels. We'll go from microscopic to mesoscopic and then to macroscopic. So on the microscopic level, we have essentially the particles. You think of molecules or atoms. We have these. We have these particles, and then the variables we're representing the motion on the microscopic level is the trajectory of particles. Let's say xj of t, vj of t. Okay, and the rules governing the motion of these particles are essentially Newton's laws. And of course, the interactions. There are different kind of interactions, which we'll get to more details later on. But this is the end of the microscopic picture. And then we take this first limit, which is usually referred to as the kinetic limit. Essentially the degree of freedom goes to infinity. Okay, and then we are having the so-called Boltzmann grad scaling, which we'll introduce later on. But in this Newton limit, we take the degree of freedom goes to infinity, and provided we also take the suitable statistical quantities of all these microscopic systems. Statistical Then we're going to get to this second picture on the mesoscopic level, which is we have these, the quantity we're interested on the mesoscopic level is the density function. Or you call the stochastic observables. And the equation that is expected to govern the evolution of these objects is the Boltzmann equation. Okay, so the idea is that, okay, so we have many particles. They have, completely different velocities and positions. And for example, even the 2 particles are close in position, they may not be close in velocity. But really, we're interested in what we're really interested in is the statistical property of this system that is, given a small range of position and velocity, how many, what is the proportion of the particles that belongs to this range. And this is given by a density function, and this is something that actually makes sense, on the kind of macroscopic picture. Okay, so this is the first limit. This is the first limit. And then after this, there is this second limit where we take the so-called hydrodynamic limit. The idea is that the solution to the Boltzmann equation actually has an equilibrium. So there is so-called global Maxwellian equilibrium, which is basically a distribution of position and velocities that is Gaussian it is a constant in x and Gaussian in the velocity v. And then there are also kind of the so-called local Maxwellians where for fixed x you have a Gaussian distribution on v. But in any case, the kind of one of the central idea of statistical physics is that in the equilibrium state, the distribution of the velocity v should be somehow Gaussian. Understand that distribution is Gaussian in V. Okay, and this actually happens in the Newton limit, where basically the so-called alpha, the collision rate, we'll define this notion later on, or in other words, the mean field, mean free path 0. Okay, and then in a pseudo limit, we're going to see these density functions as being Gaussians in a velocity variable, and then we can describe this Gaussian by these finite many parameters that depend only on t and x. Okay, since it's Gaussian in V, then these parameters of Gaussians will only depend on t and x, and these t and x are exactly the parameters of our fluid equations. Finally, we get to this macroscopic level. We have the velocity field, and these, as I said, is a function of t and x. And of course, there are other quantities, but velocity is the main thing, of course. And then these are satisfying the fluid equation. Okay. So this is kind of the big picture of these two sets of derivations. So this is maybe part A will be a description of the microscopic system. Part B will be a description of the kinetic limit. You know, how exactly do we take the limit? What is the intuition behind that? And what limit do we expect? And this is on the Boltzmann equation. And this is the hydrodynamic limit. And this is the fluid equation. So for the rest of this first half of this first lecture, I'm going to be explaining these points A to E kind of in this order. And then so that we'll have a kind of understanding of the global picture before we get to the actual statement of our theorem proof, which will only concern basically the parts A to C. Okay, so it's good. Let's see the microscopic, the particle system, let me say. So in the model, we're considering, let's say we have m particles. Okay, so n is a parameter that is going to infinity, and particles of diameter epsilon. So if without any interactions, these particles will have interaction, but if without any interactions, then they will go kind of in straight lines by Newton's law. So position, let me say, position xj of t, velocity vj of t, and dxj over dt equals vj. Okay, so dv vj dt is 0 if no interactions. Okay. Of course, when we have interaction, then this vj will change. They will change. They will actually produce a O1 change due to these interactions. So let's say, so we'll consider the various interactions. So in our work, we'll be considering the kind of the mathematically simplest example, the mathematically simplest model, which is called the Hart-Sphere interactions. Hart-Sphere model, where we think two particles interact only when they directly touch each other, and in this case they interact by just elastic collision. The picture here is that. So this is V1, V2, V1 prime, V2 prime. That is only elastic collisions. So this is the model taking our work. As I said, this is the simplest, the model that is simplest mathematically, but we'll talk about other models, briefly comment on them later on. And then there is a formula for the elastic collisions. If you think, So if the incoming velocities are v1, v2, and then the vector connecting the centers at the time of collision is omega, well epsilon is the diameter of the sphere. So if they collide, then their distance has to be epsilon. Omega is a unit vector. Then we have these outgoing velocities v1 prime, v2 prime, which is given by our elementary formula. So v1 prime is v1 minus v2 dot omega. v2 prime is v2 plus, and so way to understand it, you just think you decompose your velocities into the components that are in the direction of omega and the perpendicular to omega, and basically the velocity in the direction of omega is going to exchange with each other, and the velocity perpendicular to omega will stay the same. So this is the formula. What this formula tells us is basically kind of a reflection, with respect to the orthogonal plane of omega. Okay, so but for our purpose, this is just a formula. We'll not rely. We'll not talk about this too much. It's just we have some formula describing the collision process. Okay. As I said, there are also other kinds of interactions other than the direct collisions. We are going to have like more general like interaction potentials. Let's say we have given potential V, then the evolution instead will be given by the following. Okay, so think of V as something that decays, then this is significant only if the distance between the two particles xk and xj are within epsilon. So that's why we say these interactions happens at scale epsilon. Okay, and of course this system, the behavior of this system depends on the properties of this potential V, and essentially there are two cases where V is compactly supported, the so-called short-range case, and when V is not compactly supported, which is called the long-range case. So not talk too much about these general potentials, but let me just say that the Hart sphere formally corresponds to the case where Vx is infinity if mod x less than 1 and 0 if mod x bigger than 1. So you can think of formally as a special, this very special case of potentials, and then the kind of short range case is similar. Proof is expected. Is said to be similar to the case of Hart spheres, except for maybe some few kind of technical, minor technical points. Long-range case, where V is not compactly supported, what may require, let me just say, may require new techniques that beyond those introduced in our work. Okay, so for the rest of this series lectures, we'll be restricting ourselves to the Hart sphere case. It's the simplest, and okay, it already contains a lot. Okay, so this is the system we are looking at. We have these n particles, diameter epsilon, and then this interaction happens at scale epsilon. Let's say they are Hart sphere collisions. Okay, so next thing is say the mean free path is basically defined to be the distance particle travels before, average distance the particle travels before first collision. And this you can, by easy heuristic argument, you can see that this essentially is of the order of okay, so n times epsilon d minus 1 to minus 1. And the reason is that if you think of a particle is size epsilon, and then if you think it has time t, it travels in time t, then this is time t, and this is epsilon. So then the volume of the whole region is like a t times the epsilon to the d minus 1. And then if you think your particle, you have n particles in total, and then the total number of particles in this region is basically n times t times epsilon d minus 1. And basically if you want these this particle to have exactly 1 collisions in this time t, then this number will be equal to 1. And if this equals 1, then we get this. So t would be this n times epsilon d minus 1 to minus 1. Of course, you think your velocities are of size O1. Okay? So basically, we think that we take the so-called Boltzmann-Grad scaling. Which is, we take this value to be a constant. So n times epsilon d minus 1 equals alpha equals constant. So in other words, this mean free path is a constant size. And this basically corresponds to what is called the dilute gas case, because here n is of order epsilon to the minus d minus 1. You see, if you have n particles of diameter epsilon, then the maximum number you can fit in the unit box is epsilon minus d, but now you only have epsilon minus d minus 1, so this is a kind of a low density, essentially a dilute gas case. So by the way, so there are also questions you can ask. What if you are kind of more dense than that? And in that case, you are not expecting to have the Boltzmann equation, but you still have the fluid equation. The fluid equation is very robust. It holds for both gas and liquids. And in that case, you will probably need to develop a second route, going from the particle system to the fluids. But we're not getting to that. So throughout this week, we're going to essentially assume this Boltzmann-Grad scaling. Okay, so I think this is because the particle system is the main object we'll be studying in this week, so we'll spend most of our time talking about that. Now we have set up the parameters of the particle system, the n particles of size epsilon, and the relation, let's say, is given by the Boltzmann-Grad. And then we have set up the evolution rule of the system, that is a Newtonian, Newton's law, and the collisions given by these Hasse elastic collisions. Okay, and next thing we'll look at is the statistical, quantity statistical ensemble defined for this particle system. So let's see, So as I said before, we are interested in these density functions, which are statistical observables of the system. So for that, we'll need to set up, the distribution of these particles in the beginning. So we assume, n alpha epsilon to the minus d minus 1 is fixed. So this is called the canonical ensemble. So if you read our paper, you'll see that in our paper we're actually using slightly different version, which we call the grand canonical ensemble, which corresponds to this n not being fixed, but being a Poisson variable itself. But for the purpose of explanation, I think this is easier. Just we think of canonical version, which when n is fixed. We'll see there is some kind of subtle but technical differences. Okay, so let's say n is fixed, and then we assume the initial states of particles, this Zj 0 equals so these initial particles are independent except for the requirement so this requirement xj minus xk bigger than epsilon just means that these particles are not supposed to overlap in the beginning, but this is a purely technical restriction. We'll basically ignore that for the rest of these lectures. The important thing is that apart from this technical issue, the initial states of particles should be independent. Okay, and this is referred to the molecular chaos assumption in statistical physics, and this has been assumed, in the derivation of Boltzmann. And of course, the important thing is that, to what extent do we actually have this? To what extent is this assumption propagated in time? And this is a major part of our proof. But for now, let's just say, since we are only looking at initial time, let's say that we have, exact independence. That is, so m particle density W n 0. So this vector means the vector formed by the n particles. So this is one of renormalization constants times product okay. Let me say that this is normalization constant to make this whole thing probability measure, to make the whole thing integral 1, but this is not important. And this is a factorization, of this one particle density. And this is this restriction to the non-overlapping domain, which we'll ignore for the rest of this talk. Okay, so this is the formula for the for the whole n particle for the density distribution for the whole system. But what we are really interested in is the distribution, is the behavior of finite many particles, and this is this marginal distribution. So S particle marginal. Well, S is much smaller than n, so S is usually less than a log n to the constant. And these marginals are given by integrating this whole density in the remaining variables, which will maybe let me erase that anyway. So again, this is a vector for the S particles, where S is much smaller than n. So this is the integral and this actually you can show that when you talk about when you look at the S particle marginal where S is small, then this restriction doesn't play a big role, and essentially you are going to get something like sorry, product. Again, this is a not very important thing. We'll ignore it. Okay. So here, I didn't explain what n0 is, but n0 is just a one particle density function, and 0 is n0 xv, which is positive, and that's integral 1. And in the end, this will serve as the initial data for the Boltzmann equation. Okay, so I think this is a good description of the particle system. We have these parameters, the number of particles, and the particles go through these collisions, and then they are related by Boltzmann graph scaling. And we talk about the initial states of these particles, which are independent, with the initial density given by this one particle density n0. Okay, so yeah, let me just write this remark that canonical n is fixed, and the grand canonical n itself a Poisson variable with the expected value, let's say. Expected value being okay. So the grand canonical is taken in our paper, but the canonical case is done in the same way, except that when actually do it, you're going to see some annoying factors like 1 minus 1 over n, 1 minus 2 over n, and things like this. So that's partly the reason why we choose to work with the grand canonical in our paper. But apart from these technicalities, these are the same. Okay, so this is part A, description of the particle hard sphere particle system, and now let's move on to part B, where we take the kinetic limit. So as I said, assume we have this Boltzmann grad. Alpha being a fixed constant. Okay. Again. We have time 0 marginals, because these marginals are the quantities we are looking at in our statistical picture, because it represents the joint distribution of any finitely many particles. So we have this okay, so let me say we have ignored these indicator functions. Then, conclusion, what we're expecting what we are expecting to happen in a kinetic limit is that at time t bigger than 0, we're looking at the the marginals of the particles at time t. Time t marginals should satisfy the provocation of chaos that Okay, so this equality means that if at time t the drawing density, the drawing density of finitely many S particles is still going to be factorized to the first order. In what sense we'll make it clear later on, but to the first order we're going to have this factorization of factorization into one particle densities, and this is called the propagational chaos. Again, chaos means that these different particles are essentially independent, and if we have kind of molecular chaos assumption at time 0, then we're expecting these to have approximately have also at later times t. And then we have this NT-Z solves the Boltzmann equation. So here, let's say, of course, n goes infinity, 0. That is the Boltzmann equation. Equals sum times q. Well, this q is a bilinear collision operator. We'll see in the next part. Okay, so this is the overall, kind of a big picture of the first limit. Assume we have Boltzmann graph, we take the limit, n goes infinity, and assume we have the molecular chaos at time 0. Then at time t, in the limit, we are having this factorization at later times t, and that this one particle density is given by the solution to the Boltzmann equation. Of course, as long as the solution to the Boltzmann equation exists. Okay, so this is our goal. Actually, this.
What is the definition of V?
V here.
What's the definition?
V is a velocity variable. So n is a function of t, z is x and v. So n is function n equals n of t, x, and v. Okay. Okay. So this is the kind of the thing that we'll actually be presenting in this week. But in the first lecture, so let me complete the whole picture by explaining also what happens in the part D and part E in the hydrodynamic limits, so that to see how do we really kind of complete this whole picture going from the particle system to the fluid equations. Okay, we'll not discuss this for the rest of this week, but let me do it here. Okay, so this is part B, and then part C is Boltzmann equation. So let's take the hot sphere case. I have this and this collision integral is given by where and okay, I'm just writing this because we need to write down the Boltzmann equation at for at least one time. But you don't need to, if you're not familiar with it, you don't need to know what this is. But basically, it represents the kind of there is this it's a gain term there is last term, which will be needed in our formal derivation. Basically, this represents number of particles that moves to a particular position x and v, and this means that the number of particles that moves out from a given particular position x and v due to collisions. Okay, so we'll not rely on the exact form of the Boltzmann equation for the rest of our talk. So we'll just stop here. But let me just mention that. So there is this famous theorem of H theorem of Boltzmann that tells us that this equation increases entropy. So the entropy is the integral in minus n times log n dx dv. So this is going to increase, under Boltzmann. And essentially, the idea is that in the suitable setup, this entropy is going to increase to its maximum, and this maximum, in some sense, is achieved by this distribution that are Gaussians in V. Okay, so we'll not talk about in what precise sense, but just these heuristics. Q and n is the same function, so it's bilinear operator, because the n prime is just n evaluated at another point. Okay. Yeah. Okay. So in suitable settings, we should see convergence to equilibrium. Equilibrium is essentially those maximizers of the entropy, which are the Gaussians in V. Okay, and from here we can talk about the fourth part, which is the hydrodynamic limit. Essentially, we're talking about the Boltzmann equation in the limit where alpha goes infinity. So alpha goes infinity. So you can do the rescaling in time, so that alpha goes infinity corresponds to time goes infinity, but this is equivalent. And then what we see here is that, so hydrodynamic. So we have this, so basically, so Maxwellian is just another name to say Gaussian, and this is okay, so see this is for fixed Tx, you have coefficient here, you have a coefficient, this variance of the Gaussian which depends on T and X, and you have this Gaussian EV with a shift given by UTx, and U is a velocity field. So where, of course, so rho U T, so rho is basically a density, U is velocity, and T is the temperature, is parameters that give that decide this local Maxwellian. And what you do here, you plug in the n sets. We'll say n is something like this, and you plug this into your Boltzmann equation, and then you're expanding it in the powers of 1 over alpha. Remember, alpha goes to infinity. And then what you see is that that the Boltzmann equation is going to reduce to the compressible Euler equations for these variables. Basically solves the compressible So there has been this classical heuristic argument, given by the so-called Hilbert expansion and Chapman-Enskog expansion that not only gives the first order, the first level compressible Euler equation, but gives kind of subsequent fluid equations on higher levels. Again, we'll not talk about this in full details, but this is basically what you do in this hydrodynamic limit, where that's alpha goes infinity, and you recover these fluid equations. Okay, and this is for compressible Euler. And in the case of, let me just say it. In the case of global Maxwellian, that is this I should see scale time and get something like alpha So this converges to something I'm not writing the details, it's too complicated, but given by the incompressible Navier-Stokes equations for alpha goes infinity. Okay, so basically this is a formal, again, just a formal description of the second limit. We'll go from the Boltzmann equation to the fluid equations. And the goal here is to kind of derive the first limit, go from the particle to the Boltzmann, and derive the second limit from the Boltzmann to fluid equation. And we need to combine these two limits to complete the whole process, or go from the particle system to the fluid equations. Okay, so we still have a few more minutes, maybe for the first half of the talk. I'll describe a little bit of history. Okay, and I didn't say what is E. E is a fluid equation, but we know what fluid equations is. This is what we know. Okay, so maybe kind of the first development, before 1900, Maxwell, 1865, and Boltzmann. These are starting points of the kinetic theory, where they think the Boltzmann equation was first written down in 1865, and then there has been this subsequent supplementing theory concerning the probability interpretation of this picture, and the full kinetic theory developed in this time. And then let me mention the Hilbert, which in relation with the Hilbert 6 problem that I just described in the beginning of the talk, and specifically Hilbert mentioned, raised this specific question of justifying what is done, in these physical works. And later on we have this Chapman-Enskog 1910s, where they did essentially what we describe in the part D, this hydrodynamic limit, by performing these kind of expansions around these local Maxwellians. and so that you can formally go from the Boltzmann to the fluid. Of course, it's just a formal expansions, and the rigorous result is to wait for later. And then there has been, progress, in both the first arrow, the kinetic limit, and the second arrow, the hydrodynamic limit. So we say in the kinetic limit part, there has been work of Grad Cercignani, 1940 to 50s. Well, this was the first time where we rigorously have this Boltzmann grad limit stated, so that this justification of Boltzmann becomes a rigorous mathematical problem. And then, of course, the introduction of BBGKY hierarchy approach, which has been dominant in this field for so many years, although we are actually not using BBGKY in our proof. We'll get to that later. And then the first kind of landmark where this result of Lanford first established the validity of Boltzmann. So we say validity for, let's say, alpha equals 1 and time sufficiently small. Okay, so this is a short time derivation of Boltzmann equation. Remember, alpha is the collision rate that we described earlier, and t is the time up to which you are going to derive your Boltzmann equation. And there are subsequent works. This work of Elna Coviranti, 1980s. What extend this result to the case where alpha is less than 1 and for all time in the Euclidean setting. The reason for Euclidean setting is that because the solution to the Boltzmann equation in the Euclidean space will decay in time due to dispersion effect, and that allows them to to get the required convergence for alpha sufficiently less than 1. Okay, and of course there is this Gallagher San-Riemann taxia, where they basically revisited and actually fixed kind of some ambiguity in Lanford's original proof, and improved this revisited fixed Lanford's proof and improved. And then, in the past 10 years, there has been a huge number of works due to this group of European mathematicians, Gallagher, Bodino, Gallagher, San-Riemann, and Simonella, and many other collaborators. Let me just write Gallagher. Where they discussed kind of various models, and most notably, they were able to derive the kind of the fluctuation description around the Boltzmann solution again for a short time. So let me say fluctuations and the equations of attack particles equilibrium. So their works is pretty broad, and we cannot describe everything there. But they have done kind of a lot of work, around this analysis of various Husvy and potential systems. Okay, so let me, if I still have a few minutes, let me just summarize one thing that This is this. Okay. So I think I still need to talk about the hydrodynamic, but I don't have that much time, so I'll just quickly wrap it up. So essentially, this has been done, in the case of Euler. I'm not writing down all the contributions. It's just so many of them, but I'm just writing some of them. Some of the Nishida, 1978, Keflish, 1980, and subsequent works. Recent works, and then the next ultimate, we have this work of Damasi, Esposito, Leibowitz. Here's Bardos, Ukai, and more recent works. And more importantly, there is also these nice results concerning the weak solution to Euler and Navier-Stokes. Goes level more. We should also Lyons. Moody and Gauss and Saint Raymond, which is concerning the weak solutions. Okay, but let me summarize that. The hydrodynamic limit is much well known, and we need to match with the kinetic limit. And in that case, since we're taking alpha goes to infinity in the hydrodynamic limit, and for this we need to derive Boltzmann. With alpha goes to infinity, and t is either bigger than 1 or t also goes to infinity. Let's call it big T. The time of validity of the Boltzmann equation is either constant or at least also going to infinity. And this is the key kind of a difficulty, that has not been done in all these previous works. They either assume alpha much less than 1 or alpha equals 1 and t is sufficiently small. And the key thing here is to allow to get to the regime where alpha really goes to infinity. Okay, so I think this is the first half of the first lecture, and I think now we're ready to state our main theorem in the beginning of the second half, and then I'll talk a little bit about the global picture of the strategy of proof, and maybe kind of a brief introduction or spoiler for what will happen in the next lectures.
If you have any questions, please ask.
May I? It's a comment, may I? So, thank you for your very nice introduction. So, I have a remark to do concerning the Hilbert problem and the hydrodynamical description of a particle system. I mean, here you present the deduction of hydrodynamical equation from Newton through Boltzmann.
Yes.
But this is not the in some sense, the right way to see the hydrodynamical picture of a particle system, because you should do like Murray, no? This is the paper of Murray, in which you scale directly from Newton and
Yes.
you get hydrodynamics. The hydrodynamics you get in this way is different from the one you get through Boltzmann, for the simple reason that here, that's very nice, but contradictory in a sense, because first you take something which is for dilute gas, and then you increase the density in order to have a hydrodynamic description. As a matter of fact, the Euler equation has a pressure law, which is the one of a perfect gas. If you take a Hamilton system, particle system, you rescale like Murray did only formally, you get another Euler equation, which is a conservation of mass, momentum, energy, but the state equation is not the one of a perfect gas. So the potential enter in this. So basically, in this way, when you derive the hydrodynamic equation through the Boltzmann, you get a very, very small part in a very strange kind of limit. So the problem is still the real problem, the one outlined by Hilbert. Of course, Hilbert says Boltzmann like a mesoscopic equation. So clear that this is a possible approach, but it's not the only one. And in a sense, it's contradictory, because first you have a low density limit, then you recover high density. So this must be present in the discussion. I conclude a few seconds. If you take a linear system, you want to derive from mechanics the heat equation. Sinai-Bonimovic, billiard, very complicated. Then you get the heat equation. Then you do this. Gallavotti is a random obstacle. You get a linear Boltzmann. Then you do the hydrodynamic limit. You get the heat equation in the scale. But the diffusion coefficient is computed from one side through an ergodic theory, and the other side is something trivial, because so in my opinion, one should underline what is the fluid dynamical, what is the kind of limit and the procedure, the approach one has. This is just a remark. But this is very nice. It's not a criticism. It's just to point out that is maybe interesting to underline what one is doing really. Thank you.
Yeah, so let me say something. So basically, in our case, we are taking this, essentially we're taking an iterated limit. You can basically, our result corresponds to this kind of specific regime where you are close to the Boltzmann graph, but you deviate a little bit by allowing this alpha to go to infinity. We'll see basically, we'll do the spoiler. Basically, alpha is log n to the 1/2. Something like this. So you have a pretty narrow range of scalings in this picture. So of course, there are more kind of other scaling laws. Like you deviate a lot from Boltzmann. Like if you allow this alpha, n to be a different power, n to be even like epsilon minus t, and in that case, I don't think it's even possible to go through the Boltzmann to derive the fluids. However, the fluid equation is still valid in this case. So of course, in these settings, we do need to have kind of basically completely different approach. Yeah, so this is the point. Yes?
So it starts from hardcore gas and then... So if you start from the hardcore gas and then pass through to all the way to oil, compressible oil, what can you say about the final pressure? Does which part of the microscopic part still retained?
We haven't thought about this kind of we direct kind of link the parameters in the fluid setting directly to the original original particle setting. Like honestly, we haven't thought about it. So our work has been focused on the transition from particle to Boltzmann. But this is an interesting question. Like whether some of these quantities can be interpreted in Dirac in the particle system. So this will be something very interesting for next step of study. But we are not doing this at here.
What I'm worried about is that
Yeah.
when you go from Hart sphere all the way to Euler, the internal energy should come purely from just the kinetic energy. So the particle system has nothing to do with the underlying Hart sphere. So if you go to Boltzmann, then from Boltzmann pass to Euler, can you see this phenomena of that the Hart sphere still retains its property in the Euler?
I'm not sure what exactly your question is. I mean, can you be more specific about the mathematical, what would be a mathematical, object you're talking about?
Maybe how should I say this? So if you have the compressible Euler equation, if you look at the pressure, not the pressure, the internal energy, it has supposedly it has two interpretations. Not two parts. One comes from the microscopic dynamics, and one comes. The internal energy has two parts. One comes from the microscopic kinetic energy, and the other part comes from the interaction. If you have the Hart sphere model, in the limit, what happens is that the part that comes from the Hart core interaction actually goes away, and what you get is purely the kinetic part.
You mean the kinetic energy is conserved in the collision?
It's what energy is conserved.
Okay, so let's restart. First, let's state our main theorem. So okay, so assume we are, in the domain. Our domain is either Euclidean space in dimension bigger than 2, or the torus in dimension 2 and 3. I mean, there are some technical reason why we need to restrict to the dimension less than 3 in torus, but that's not very important. Okay, so we have the parameters alpha and t. T is the time of validity of the Boltzmann solution. And we assume that alpha times t less than this less than. Well, again, there is a reason for this log, but for our purpose, we just need to see that it can go to infinity. And then is a strong solution to Boltzmann. Okay, so let me summarize. So we have a domain. We have these parameters alpha t, which is up to this log. We have a fixed solution, like strong and nice solution on interval 0 to capital T. Of course, the solution is supposed to be belong to some certain space, basically the local opposing space of the Boltzmann equation. Okay? And then we have the Boltzmann grad. Okay? The conclusion. We have the propagation of chaos plus the derivation of Boltzmann on ZOT. That is so Fs is a S particle marginal. So minus this factorized product of one particle density, and the one particle density is approximated by the solution to the Boltzmann equation that we have in the upper half board, and the error term measured in L1 is going to 0. Of course, epsilon goes to 0. Alpha equals a constant.
Not the same of the other.
Sorry?
This alpha is not the same of the previous alpha.
Yeah. Sorry. Gamma. You're right. Okay, so this is, and of course, as a corollary, we also have, so since we're allowing this alpha to go to infinity, we're allowing this t to go to infinity, we also have the, derive the fluid equations in the iterated limit sense. But, of course, as said, we'll focus on the proof of the first result, the Boltzmann. Okay, so the plan is that for the rest of this week, we'll be talking about the proof of this single theorem. So the plan is that today, for the rest of the day, we have an hour. We'll be talking about kind of start with a very kind of physical, proof of this fact, and this will suggest to us, some, few kind of crucial intuitive points, and then we'll expand on that intuitive points, and then we'll get a kind of partially rigorous proof in the short time case where alpha is less than 1. Let's say y is much less than 1, or maybe t is much less than 1. And then we'll talk about, what is the key difficulty, and what is the key point that is needed to address a long time case, and that will serve a kind of a spoiler for the next 4 lectures. And then on Tuesday and Wednesday, my collaborator Martial will talk about the setup, in the setup and ansatz in the long time case, and then essentially he'll reduce kind of the whole proof to a specific the proof of a specific combinatorial fact, which is associated with a new kind of notion we introduced called molecules. And then in Thursday and Friday, I'm going to present the analysis of those structures, which is follows a very complicated algorithm that we'll present. Okay, so today we'll do some kind of something on a heuristic level. Okay, so ideas. So we start with a very kind of naive, quote, physical kind of argument. We want to answer the following question. Let's say, we have a propagation of chaos. Because the molecular chaos assumption is a kind of natural thing that we think at least initial states of the particles are kind of independent, and then later times that's okay, so we think they are also independent. So we'll see, if we think they are independent, then can we deduce the Boltzmann equation from that? So this is the first question. So a physical justification. So can we get derive Boltzmann from assuming the molecular chaos? Okay, so this is the first thing we'll do, and then from there we'll see some of the intuitive points that will be important in the proof later. Okay, so know that the Fs, let's say Fs T Z1 Zs is S particle marginal. F1, of course, Z, this is one particle density. Then let's say formally what do we do? How do we calculate the dt of this F1? Again, formally, to calculate dt of F1, let's just look at like F1 of t plus delta t xv. Okay, we look at this quantity. Okay, so this is basically the the density of the particles at time t plus delta t at location x and velocity v. Okay, so we think of these when does a particle arrive at the point x and velocity v at this time t plus delta t. So it can arrive in two cases. So either it arrives at this x and this v without doing any collisions, or it arrives at this x and at this v kind of with a collision, let's say in this time t plus delta t. Okay, so basically this is equal to no collision t plus delta t xv plus a collision. Again, what I'm saying here is completely non-rigorous, but it tells us something. So there's a non-collision part and the collision part. So then it's clear if this particle has non-collision, has no collision, then it just goes linearly. So we have F1 no collision of t plus delta t xv. It's really just if it just moves linearly, then it becomes at point x at t plus delta t means it was at the point x minus v times delta t at time t. So F1 collision of t, and then we have x minus v times v. Okay, so. Yeah, this is what we mean. Like this is kind of the contribution of the no collision. Yeah, yeah. Okay, and then the second term. Let's look at the second term. The first term is essentially a transport term, and then we look at the second term. The second term here is t plus delta t xv. Okay, so it basically means that we think of it as a probability, kind of the contribution of particle 1 having collision with another particle 2. Okay, so what is the contribution of that? You see, a particle, we have a fixed particle 1 here that collides with another particle 2, and that particle has essentially n choices. So particle 2 has n choices. I mean, strictly speaking, it's n minus 1 choices, but this is not important. And then if we fix particle 2, then the probability of 1 colliding with 2 is given by this basically epsilon to the d minus 1 integral. So let's say, so since the particle 1 is at position x and velocity v, have this v minus v prime of f of let's say t f of 2 t x x v x tilde x v x x v x v prime d d omega. Sorry, this is the collision. This is the collision to produce v. So this is v1 prime d omega dv prime. Okay, so let me explain what that is. Basically, the picture here is that here, in this term here, in this F1, so some particle 2 collides with particle 1 to send it to velocity v. Okay, so this is what happens because you're considering the contribution of the particle that gets to velocity v after collision. Okay, so let's see the so the kind of incoming velocity of particle 1 and 2 is v1 and v1 prime, and outgoing velocity of 1 and 2 is v and v prime. And then the v1 prime, v prime satisfy this formula, the collision formula we had before. v1 is v minus and v1 prime is v prime plus, and omega is essentially the so epsilon omega is the vector of the two between the centers at collision, and omega is arbitrary unit vector here. Okay, so basically, if you to see what is the contribution or what is the probability of a particle 1 colliding with particle 2, you measure all the choices of particle 2, and you have this factor n to epsilon d minus 1. From the heuristics, that you have a collision happening between two particles has probability epsilon d minus 1, and the precise contribution is given by this integral. And here, the key thing here is this quantity. Okay, because in order for a collision to happen, you need the velocity of 1, incoming velocity of 1, to be v1, and incoming velocity of 2, of particle 2, to be v1 prime, and the density contribution of this term is given by the the 2-point density at time t at x v1 and x and v1 prime. Okay, this is a thing, and now if we make the molecular chaos assumption,
Velocities 1 and 2 are v1 and
The incoming velocity at v1, v1 prime. So this is in the gain term. This is our outgoing velocity. V is our target velocity, and v prime is the other. Okay. So now if we assume a molecular chaos, then F2 T x v1 x v1 prime is F1 T x v1 F1 T x v1 prime. And then we get a closed equation because the right hand side, I mean this term at least will be a product of F1, and the left hand side is F1 because we are calculating the derivative of time derivative of F1.
Will there be a time factor T?
Good. There is because there is a let's say a t from t plus delta t. Yeah, because we're talking about integral, not derivative. Okay, good, very good. So dt tilde. Okay, so yeah. Okay, and then we have. Let me just write it down. Is f1 t xv is n epsilon d minus 1, which is alpha.
Excuse me, you are assuming the molecular chaos at a positive time.
Yes, of course. We are assuming this, and of course, I mean, this is a completely heuristic derivation. Like, we are assuming this.
This is the usual heuristic derivation.
Yes. Yeah. Okay, and then we have this integral from t plus delta t, so r d times s, and then we have this f1 t x v1 f1 t x v1 prime d v prime d omega dt tilde. Okay, so this is this term, and this takes care of this term. And of course, we subtract later. We subtract when divide by delta t. We take a limit. We just calculate the contribution of this to the time derivative. Okay, so now what about the first term? The first term is the first term non-collision. The first term non-collision is given by this. And okay, so this is already the density at time t, but then we have this non-collision assumption. So we should really call it as the F1 at the density at time t minus the F1 collision at time t. So on the other hand, we have F1 time t, and then x minus v delta t. V is F1 t x minus v delta t v minus F1 collision at t x minus v delta t v. And this term means the contribution where you, at time t, you are at the velocity v and you have another collision. That means your particle 1 has velocity v at time t and it collides with another particle at time t that has some other velocity. And then this is the same thing as what we're deriving here, again assuming molecular chaos, but then we are just this v1 prime should be replaced by the v and v prime. So in the end, we get similarly, so this is almost equal to is So we can put together everything. Remember that so we have f1 t plus delta t. Okay, so xv equals f1. So we have the collision and non-collision. The collision term is given by this first term. The non-collision term is given by this minus this. So this will be the gain term, this will be the loss term, this will be the linear transport term. f1 of t x minus v delta v plus this integral. It's too long to write down. Okay, so let me call this as integral 1. And this as integral 2. And then we take the difference. If we divide minus f1 of t xv, so this is minus f1 of t xv, and then we divide by delta t. We take the limit. You see this term turns into the v dot grad x, and then this term integral 1, since the integral here is the integral from t to t plus delta t in time. If you divide by delta t, you get rid of the integral in time, and then you just get this the v and omega integral 1, v and omega integral 2. So let me just say in the end, we get omega is arbitrary. It's arbitrary, unit vector, because omega is the when you have the time of collision, this vector between the centers is epsilon omega, and in principle, if you fix a position of one particle, this other particle can be colliding within in arbitrary direction. So this omega is arbitrary. Yeah. So so actually, what happens here is that this when we're integrating omega, then this omega is is arbitrary, and then it's basically the density function. Like the density function does not depend on the choice of omega, and then you get this integral kind of. I mean, it's really like when we talk about the delta function, delta of x minus x prime minus epsilon is like delta of epsilon to the some power times delta of omega minus 1, and this is really just a delta function of omega on the unit sphere. Okay? Yes?
So that will lead to the weight in the integral.
This is just a delta function. Like you integrate, you integrating omega in the unit sphere, so you just get the unit, the surface measure on unit sphere. I mean, so for our purpose, this is the exact. Well, you have some exact form. I mean, whatever you have there is not completely not most important. Like you may have some ways, but it doesn't affect our heuristic argument. Okay. Okay, so then we summarize. We get yeah, of course, there are some details involving the calculation. I'm not presenting the details of that calculation because this is not the most important intuition I'm going to talk about that we get from this heuristic argument. And then let's summarize. We get this dt of f1 equals v dot grad x f1 plus this first integral. Just write f1 tx v1 f1 tx v1 prime minus txv and this is a gain term. This is the last term. Okay, so essentially what this heuristic argument tells us is that, so this tells us if we have independence, then we have the boson equation. This is one thing. Another thing, which is actually more subtle, is the following.
Excuse me, I don't understand. I mean, the gate term is V1 and V1 prime. It should be V prime and V1 prime.
Sorry, I mean, V is this, V prime is this, V1. Okay, I mean.
V prime is the pair, usually change.
Okay, I mean, yeah. Never mind. So the more subtle point is the following, that you really do not really need complete independence in order for this formal derivation to work. What we really need is need the particles 1 and 2 to be independent at time t. Okay, to derive this Boltzmann equation. Okay, now the thing is that these particles 1 and 2, they are supposed, so let's say time t minus 0, let's just to be precise, they are supposed to collide at time t. Okay? So in other words, we do not really need all the particles to be independent. We only need those particles that collide at time t to be independent at time t minus 0, at the left limit of time t. Okay? So what this means is that, so in particular, if 1 and 2 are not independent at time t minus 0, then they must have a collision or connected by collisions in the time interval 0 t. Okay, so this is what happens, that would violate our independence, naive independence picture. And then the idea is that ultimately we're going to show that contribution of this phenomena is negligible and it vanishes in limit. Of course, this is much not as easy as what I'm saying here, but this would be the starting point. Okay, and let me show you an example, when does it happen that these two particles, they have a collision, they're already connected by collisions in time strictly before t, and then they have another collision, they're supposed to have another collision at time t. So we'll use different colors to draw different trajectories of different particles, and then you'll see So let's say in this picture, this orange one is called the particle 1, and this green one is called particle 2. So 1 and 2 first collide at this time. Okay, so there's a collision here. Let's say. And then the blue one is called particle 3, and the yellow one is called particle 4. Okay, so what happens here is that 1 and 2 collide, and then 1 further collides with 3, 2 further collides with 4. And this is an example. So let's say this is, okay, roughly speaking, this is time t. Okay, so then between time 0 and time t, these particles 1 and 2, they are already connected by collision. Actually, they are already colliding themselves, before time t. Okay, and then after some other collision happens, now at this time t, these particles, they collide again. Okay, so let's show it here. These particles, they collide at time t. Okay, and then they go forward. So whatever they do afterwards. Okay, so this example where the two particles 1 and 2, they are already connected by collisions, before in the historically, and then they collide again at this time t. And this is an example which is called a recollision. So this is a, and the recollision can be interpreted as this diagram, the diagram for my collision, to have a cycle here. That this thing collides, and then after some time they collide again, and this forms a cycle. So basically, recollision equals cycle, and this is the thing that we want to. This is a pathological, kind of phenomenon that we want to avoid in order for our heuristic derivation to work.
Excuse me, recollision is defined only in this situation, or you can have a more complicated story in the past, and then you have again another collision.
Of course, you can have.
It's still a recollision.
Of course, you can have arbitrarily complicated diagram below, as long as you have a cycle and a constant recollision.
Recollision is generic.
It's arbitrarily complicated. Okay. But of course, for demonstration, we're just drawing this simple example.
Can you have maybe 3 of them colliding at the same time?
Sorry.
Can you have 3 particles?
3 particles colliding at the same time, this is not possible in the Hart sphere case. Well, in the potential case, you need to do it. It's annoying, but you need to do it. In the Hart sphere case, it's simplified, so this is not possible. 3. Okay, so let me summarize. We need to show recollisions are negligible. And of course, that would imply, propagation chaos as we need it. And this will imply the Boltzmann. Okay, so I think this is what we learned from this heuristic argument, and from the kind of the possible violations, possible scenario violating this heuristic argument. And now, because these notion of recollisions will be very important in our proof, and of course the notion of chaos, notion of what things can be factorized, what things are independent, what things are not, again will be very important in our proof. Okay, so for the rest of this lecture, we have 20-25 minutes. So we present the proof, and kind of more rigorous, kind of a still partially rigorous proof in the short time setting, in the theorem of Lanford and of Gallagher's theorem and Texia. And we'll see, in that case, we're just basically doing one expansion, and distinguish the leading and subleading terms, and then we'll talk about what happens in long time case. No. Before time t, these are connected. But at time t, you have a further collision, and this will count as a recollision.
But this 1 and 2 collect twice.
Well, they collect twice, yes.
But it is possible they are not collided previously, but
Yeah. So one is if imagine this not one collides with, imagine this 3 collides with 4, then you have the same picture. One collides, 3 collides with 4, 1 collides with 3, 2 collides with 4, and they connected, and then 1 collides with 2. This is also possible. I'm just showing this is an example. Okay. Okay. So let me present the semi-rigorous proof in the short time setting. the idea, why we can do this short time setting is because we can perform essentially an expansion. Okay, so short time case. So assume, let's say alpha equals 1, and the t is sufficiently small. The point is that perform an expansion of this F1 of this one particle density that is convergent. That is power series of T and is convergent. The thing here is that this T is sufficiently small, and so this power series is convergent. Okay, so this is basically what has been done in the work of Lanford, in the work of Gallagher, Zimmerman, Taxi, and all these similar works. The key thing is that we are performing expansion. So there is this kind of a constant term. There is a linear term in first order term in T, second order term in T, and third order term in T, and so on. And these different order terms are indexed by the kind of the collisions that actually happens in this picture. So let me say that we'll do the collision history expansion. Of course, historically, people have been doing BBGKY, but as I said, our work is not using BBGKY, so we're using these kind of more concrete expansions. So just for the purpose of motivation, we'll just also do these collision history expansions, in the short time case. So basically, F1 Tz is a sum. I mean, again, this is there are lots of details to be added if you want to make this fully rigorous, but this is just on heuristic level, so collision history. Okay, so what this means? This CH is a combinatorial structure counting all the collisions related to particle 1 that happens from 0 to t. Okay? So what we mean by related means that if 1 collides with 2, then of course we count this collision. But then if 2 collides with some 3 previously, again we count this as collision. And then 1 collides with something, if those something, 1 collides with something, and those something collides with other things, and those other things collide with something else, then we count all these collisions, we put this into this combinatorial structure CH. Okay, and then of course there are infinitely many, there are countably many, combinatorial structures CH, and then we are going to estimate, what does this mean? This means, the contribution to the 1-point density under the assumption that all these CH happens. Okay, we're going to calculate the contribution of this, and we'll show that it's convergent series. So, let's do 2 examples, and you'll see what I mean here. Example 1. Okay, so before examples, I should say that this is not quite the correct thing because you have the loss term, and this loss term will come, by introducing this negative term will remove kind of certain terms corresponding to virtual collisions, which is usually called overlaps in terminology of kinetic theory. But it will be complicated to also introduce that, and this term, the behavior is pretty similar to these positive terms. So let's just let's just simplify things by pretending that we only have this positive term. In reality, you have negative term, but okay. Okay, so let's say if we have this example of a 3 collision. So let's say you have a 1, sorry. Okay, so let's call this particle 1. And let's call this particle 2. So this particle 1, this is also particle 1. The same color is representing the same particle. This is particle 2, and this is particle 2. And this is particle 4. And this is particle 3. Okay, so what this graph means, the CH means that 1 collides with 4. 1 collides with 4. And then 1 collides with 3. This is still 1. 1 collides with 3. 1 with 3. Then 1 collides with 2. 1 collides with 3, and then 1 collides with 2, and then you goes out at this, and then with 2. Okay, so this, you see this example without a recollision. So this you have 3 collision that doesn't form a cycle. So this is something without a recollision. We'll see that this will be, the contribution of this term will be O1. Okay, so let's see why this would be O1. It's because, okay, so then the contribution, it's basically, you're integrating. Let's say since you're fixing the outgoing position velocity of 1. But let's say if you want to measure the density in L1 norm, which is the simplest case, same thing we can do, then we can integrate that. So contribution in L1 norm will be the following. You integrate in all the the 4 xj's and 4 vj's, kind of the initial velocities of the 4 particles 1, 2, 3, 4. Okay, so integrate something. Okay, so let me write, dx1, dv1, dx2, dv2, dx3, dv3, dx4, dv4. Okay, and then when you integrate, so first of all, you're fixing this particle 1, fixing particle 1, but these other particle 2, 3, 4, each can be arbitrary. So you're fixing the label of these particles, which gives you this n to the 3rd. Okay? And then you are having the initial density, which is a factorized thing, like product n0 xj vj, which is not important. The important thing is the fact that you are having this collision. You are having these collisions means you are having an indicator function. The initial x1 v1 x4 v4 must satisfy some restriction in order for this collision to happen at all. And then you have this indicator function. And then you know that after this collision, you have this outgoing velocity. Then this and the velocity x3, v3, again, they'll satisfy some restrictions in order for this second collision to happen at all. And you have third collision. So basically here, you're having these indicator functions of all collisions. Okay, so formally speaking, the contribution of this collision history to the whole to the one particle density is going to be given. Let's say if we measure L1 is going to be given by this integral. Let's just write the product dij dvj instead of writing this. And let's calculate what's the size of this integral. Okay, so let's erase this. In the no recollision case, this is actually pretty simple to calculate. Fix x1 v1. Okay, in this picture, let's say we fix x1 v1. x1 v1 is in a compact set, doesn't matter. Okay, we integrate, first collision dx4 dv4, because x1 collides with 4, so fix this, and then the vx of v4 has to be in some set in order for this first collision to happen, and this set has measured epsilon d minus 1, as we already seen from the very beginning. Oh, here is the picture, and actually this is less than epsilon to the d minus 1 times t. Remember, the collision is happening between 0 and t, so we have this factor t here. Okay, so this is the first thing. And let's say we fix x4 v4, because this is we can view this as an iterated integral. We first have the integral in x4 v4 is given by this, and once x4 v4 is fixed, we can integrate in x3 v3. So for x1 v1, x4 v4, we have integral second collision dx3 dv3, again less than epsilon d minus 1 times t. The reason is that once you fix these velocities, then this outgoing velocity is also fixed, and then this x3 v3 is supposed to collide with this fixed outgoing velocity, and no matter what this outgoing velocity is, the probability is always bounded by epsilon d minus 1 times t. And finally, x1 v1, x4 v4, x3 v3, we have a third collision dx2 dv2 times t. And this gives you a contribution of this collision history to the F1, to the one particle density, and then we get okay, so we have CH1, let's say, N3 T, epsilon d minus 1 to 3 times T3. Let's say alpha equals 1, so this guy is equals alpha. This is equal to T3. If you have 3 collisions without recollisions, then your contribution is O of T3. And you see if T is sufficiently small, this will be convergent as a power series in T, and then you can sum them up. Okay, so this is a case example with no recollisions. Let's see for the rest few minutes. Let's see an example with recollisions, and we'll see you are gaining a power of epsilon in that case. The reason is okay, what this means, this is particle 1, and this is particle 1. And there is a particle 2 here, the yellow one, particle 2, it's particle 2, and the particle 3 here goes like, okay, so here the CH means that, so 1 collides with 2, and then 1 collides 2, and then 1 collides with 3. 1 goes out with 3, and then 2 collides with 3. Okay, so this is the case. You see they form a cycle, which means you do have a recollision. And what do you have in that case? The contribution. Again, you have a particle 1 being fixed, and then you have 2 other particles 2 and 3. So you have an n to the 2 times integral, again, the product of n0, the indicator function of all collisions. product j dxj dvj. Okay, what happens here is that fix x1 v1, fix x1 v1. Again, when you integrate x to v2, your 2 just collides with 1. Whatever you do is just integral dx to dv2, the same, epsilon d minus 1 times t. Now, when integrating dx to dv3, things become different. If you fix x1 v1, x2 v2, integral indicator function of d dx3 dv3, you see, first of all, 3 will have to collide with 1 to produce this, okay? And if you only have this assumption, if you only have this collision, then we'll give you like epsilon d minus 1 times t. But now, not only you have this, but after these 3 collides with 1, this outgoing velocity of 3 is still going to have a collide with another fixed vector, which is 2, because this vector is fixed, like the velocity of v2 is fixed, but then this particle 3, it collides once, and it must collide another time, and this second kind of collision is forced, and it gives us this extra, smallness of measure, and then in the end, it gives at least an extra factor of epsilon. Okay, and here we don't even need this t, so let's just okay, so this is the thing. This is the difference between the case of no recollisions. Well, in each integral, you have exactly this bound which is sharp. And the case of recollision will have each recollision. Okay, let's be careful. For this one recollision, you're going to get an extra factor of epsilon here. Okay, so I'm not saying for each collision we are getting an extra factor of epsilon. This is too much to require. But for this one collision, we do get 1 factor of epsilon from here. Okay, and then you put together, you see you have 2 factors here. Again, they cancels with the n squared factor here. You get the power of t, and then you get epsilon. So in the end, let's summarize. Okay, so maybe if I have 5 more minutes, let me just summarize. Okay, if you have a collision history with m collisions and no recollision, contribution will be t to m. If you have m collisions and has recollision, contribution is O t to m minus 1 epsilon. And now, again, on the heuristic level, if t is sufficiently small, this power series converges in M, and then you get these terms, non-recollision terms, which turns out in the end it will match exactly term by term the Boltzmann expansion, and those recollision term that vanishes when epsilon goes to 0. Okay, so this is a kind of semi-rigorous proof of the short time result.
You haven't talked about if 1 hits 2 and then at some time 1 hits 2 again.
What do you mean? Like you have more than many recollisions?
No, I'm just if you have 2 particles 1 and 2, it hits.
It's
1, 2 hits, and then after some time 1.
Yeah, this is the same argument. You still have a cycle, and your proof. You still in one of those integrals you'll get an extra epsilon. I'm not necessarily the first or second, but in one of them you'll get an epsilon. Okay, so now maybe if I just give me 3 minutes, I'll wrap up and with the difficulty, what happens in the long time case. What happens in a long time case? So first of all, this t is bigger than 1, so you cannot expand. There's no way you can expand in this way because it will never converge. Cannot expand on 0t directly. The idea, of course, we divide 0t equals union of L minus 1 tau, L tau, so L from 1 to big L, where tau is smaller than 1, but L is very big. Let's say one half. Okay, then the idea is that you are going to divide your time interval into tau, 2 tau, 3 tau, 4 tau, and so on, and try to do an induction argument. However, in doing this, there are two kind of key difficulties, which I'll just say here as a spoiler. I'll now explain, because Xiao will explain in his lectures on Tuesday and Wednesday. But the question is, the particles will not be independent at L tau, L bigger than 0. And second is that how do we see the time irreversibility of Boltzmann equation? For example, if you follow this picture, if you go from 0 to tau, fine. But then if you go from tau, you can go from tau to 2 tau. You can go from tau to 2 tau, or you can try to go from tau back to 0. And then if you don't really see the irreversibility at some point, then you are going to get the obvious contradiction that this will never going to work. Okay, so in fact, we'll need to answer these questions. So how do we address the non-independence of the particles at later times, and how do we devise a mechanism that distinguishes from going forward in time and going backward in time to see the irreversibility of Boltzmann? It turns out that these two questions can be answered by one single thing, which is the ansatz that will develop for the Kuhlmann expansion at each time, and this ansatz, highly depends on L. It actually, this ansatz evolves, in different time when L progresses, and this actually allows us to find the substitution of independence, and allows us to find substitution that really generates this irreversibility.
There is also the size of the marginals, right?
Size of what?
I mean, when you pass from 0 to tau,
yes,
and you want to pass from tau to 2 tau,
yeah,
the bounds for the estimates you have on the marginals are destroyed, no?
We don't. You see, one key thing is that we are not proposing any specific estimates on these marginals. We're proposing an exact ansatz of the marginal that is equal to some very precise summation of combinatorial structures plus a tiny term. So it's very important that we do not rely on any estimate, like LP estimate of these marginals, Kuhlmanns, and they will not work. We really need to devise some ansatz, which we'll see on Tuesday and Wednesday.
You have the probability estimates.
It's, well, okay, so
no, you can.
Well, let me show you. It's
Anytime my question.
Let me show you what this means. This means that we are, well, it's an equality. It's not an inequality. It's like the, Fs L tau is a sum of the product of Fa times this cumulant EH, this cumulant, and this EH is a sum over the structures on 0 L tau of something plus tiny error. We don't care. You see, this is the thing we propagate, and then once we prove this, only after we prove this, then we start to do probability estimates. Thank you.
Any questions?
So I think therefore our second most results, we should also need to say some irreversibility of time.
Well, I don't think it explicitly appears in a proof because they just do expansion. Like from expansion, you just see the terms in Boltzmann expansion, and that's it. So it's a short time. Like conceptually, you just go from 0 to t directly. So there is no way you can turn back. And yeah, true. But I mean, I don't think this is explicitly seen in a proof.
Could you also explain a little bit about how did you get epsilon greater than t in your last step?
Yeah, it's because you have extra condition. Like you have, if you don't have the top one, the top collision on top, then you just have epsilon d minus 1 times t. But then you have, like you're integrating something, but you are restricting that function to an even smaller set, and you get a smaller measure. That's well, okay. So I mean, the t is epsilon is much smaller than t. So I mean, yeah. So let's say we put a t here. I mean, this is not important. Once you have epsilon, the t is no longer important.
Any other questions? Okay, so you know, let's send our speaker again.